All right, today I want to talk about something, momentum, that is used so often in the English language and where it comes from in physics and actually working the physics with it. Now, momentum in physics is the product of an object's mass times its velocity. Now, in the English language, momentum is all about how hard it is to stop something. If a sports team just scored a goal going into halftime, we'll say they have all the momentum right now, and it would take a lot of, in other words, it would take a lot of force or a lot of something to try to stop them. You're doing well in school, you built up some good momentum, easier to keep going once you've already done something. That's the idea of momentum. In physics, momentum is mass times velocity. It is somewhat related to Newton's first law, inertia, right? It's pretty much directly related to that, inertia. A lot of mass, a lot of velocity, hard to stop. Little mass, little velocity, easy to stop, or some combination of the two. In physics, it's just mass times velocity. That's the easiest way to think about it there. Units. Kilogram meters per second. You could also change that around to Newton's times second, so either of those will work. Now, this concept of momentum is just a mathematical equation, but where it comes in very useful is in collisions. In any collision, momentum is always conserved. It's never created nor destroyed. Okay, it's only transferred from one object to another. Even though you might lose kinetic energy or some energy might be converted into work, momentum, this mass times velocity, always holds. If I'm just going to do a quick example problem, just calculation of the, my momentum of the car, well, that's just, P equals mv here, and so P is 750 kilograms times 21 meters per second, and that gives you a momentum of, using sig figs, it's 15,750, but using significant figures, it's 16,000 kilogram meters per second. So kilogram meters per second would be my momentum there. Now let's talk about actually what type of collisions there are, because that's where it really comes in useful. Three main types of collisions, and all of them really can be used from this elastic idea right here. Pretty much everybody can be traced back to that, and I'll show that in a derivation here in a moment. But you have elastic collisions. That's where kinetic energy is conserved. No kinetic energy is lost. The objects perfectly, if you will, bounce off of each other. So if two things are coming head on and they hit and bounce off of each other, or something stationary, another thing hits and they bounce off of each other, that is an elastic collision. If it is perfectly elastic, which is what we're going to have to deal with here, then there is no compression of the two objects. In other words, there's no work done on the two objects. Whenever, if you compress some distance delta x, then work's being done, you're going to lose some kinetic energy. So they perfectly bounce off of each other. The inelastic kinetic energy is lost. Some of it's converted into work, which then is translated into heat generally. And the objects, stick together to some extent. Now, most collisions are kind of a combination of elastic and inelastic, somewhere in between. We can only deal with right now in our class either perfectly elastic, they perfectly bounce off of each other, or perfectly inelastic, they completely stick to each other. Okay, and the last type is explosion. Now, the explosion, things are stuck together in the beginning, and then they separate. So initially they're just stationary, and then they separate. Equations for all of this. Elastic, you have the momentum of object 1 plus the momentum of object 2 all in the beginning, right? Initials. Equals the momentum of object 1 afterwards plus the momentum of object 2 afterwards. In other words, momentum is conserved. The total momentum of both objects beforehand equals the total momentum of both objects afterwards. Inelastic collisions. The two objects are separated in the beginning. So I have the momentum of object 1 in the beginning and momentum of object 2 in the beginning. But afterwards, in the final part, if you will, they are completely stuck together. So they have the exact same velocity, and we're going to add their masses. In other words, they have one momentum here. Their final velocity times their two masses added together. In an explosion, we lots of times will consider their initial velocities to be 0. So this entire left side of the equation goes away, only leaving me with the right side. So it becomes the negative, if you will, negative m1 vf, right? So the negative momentum of final momentum of object 1 equals the positive momentum of object 2. Now this negative sign is very important because if two things are at rest, For momentum to be conserved, if one thing goes to the left, the other thing must go to the right. They have to go in opposite directions. If they go the same direction, they both have positive momentum, right? And it's not conserved. It has to add back up to equal 0 because the two objects, their initials, were 0 if they're just sitting there at rest. Now, the equations that I showed you on the previous slide were all for just two objects, but it works the exact same way if you have 3, 4, 5, 6, 7, or many, many more objects. There would just be a lot more initial momentums and final momentums in whatever equation you're using, right? If it's the perfectly elastic one like this one, you have a set of momentums for each object, 4, 5, 4, 5, whatever on the initial and the final side. If it's an inelastic, you have a whole bunch of stuff on the initial side, all those different pieces, momentums added up equals all the pieces masses add together times their final velocity, right? In an explosion, you're just going to have a lot of more pieces. Now, in an explosion, things get a little bit more hairy. And generally with explosions, you're going to have more than two pieces if you're thinking about some sort of combustion reaction, a chemical reaction occurring that then causes pieces of whatever that object is to explode outwards everywhere. Gas is getting released because that is matter. We have to account for that if we're dealing with a chemical reaction. But we're not going to go there right now. We're just going to deal with the two-object idea, because if we can deal with two objects, you can deal with the more complicated things later. Now, both of the other equations can be derived from the elastic equation. The elastic equation is kind of the equation that shows conservation of momentum, because it's all the different individual momentums added up. If you here I have 2, I might have 3 and 4, equals all the final momentums added up. In an inelastic equation, your final velocities become the exact same because you're stuck together, right? And so we factor out the VF. That's why we get VF times, in parentheses, M1 plus M2 close parentheses, right? In an explosion, we're simply saying that the two objects are stationary in the beginning. So that means if your VIs are 0 here, right, your initial velocities, they just go away. So I have 0 momentum in the beginning. They're just sitting there, all right, equals M1 VF plus M2 VF. And then I just simply bring negative M1 VF to indicate they have to go opposite directions. That's critical, M2 VF. So then I just bring it over to the other side there to get that. Now, if the two objects were moving, let's say the two objects were stuck together, they're going to explode outwards, and they were actually moving in the beginning. Well, their initial velocities were the same because they're still joined up, right? So I'd have VI times M1 plus M2. Initial velocities are the same. That's why VI times the addition of the two masses equals now M1 VF plus M2 VF. Right? They explode outwards from there. So that's if they are moving in the beginning. The three equations that I gave you on the last slide, please make sure to add them to your equation sheet. And then I'm going to solve a few problems for you in the next set of videos.